Hello, everybody, and welcome to Echo Live, our regularly occurring Wednesday program coming to you from the Michigan Science Center's Echo Distance Learning Program. Today, we're going to dive into some spooky science as we investigate the states of matter. Now, as cool as this filter looks, it's maybe not the best for presenting some of the really cool experiments that I have to show you today, but just for fun, I thought I'd show it to you anyway. But let me go ahead and turn that off. While I get our color back going here in the Echo Studio, why don't you go ahead and introduce yourself on whichever program you are tuning in on. I can see that we have some familiar faces joining us on YouTube, some friends starting to tune in and to join us on Facebook. So go ahead, let us know who you are, where you're watching from, and if you have a guess about what we might be talking about today based on what you see on my table so far, or maybe what you know because of our title slide there. How does this all relate to the states of matter? Now, today we're going to be talking about dry ice. And dry ice is something that we've talked about quite a bit on Echo Live, but today we're going to dedicate an entire 30-minute program all about dry ice because it is one of the coolest things, literally and figuratively, that we get to work with here at the Michigan Science Center. And it's really one of the best ways to demonstrate how the states of matter change based on temperature or based on adding or taking away kinetic energy or heat. Now, let's see, we have a couple of friends starting to tune in. Hello, Evan from Texas. Hi, Haley. All right, hi, Mikey. Everyone's starting to tune in there. Lots of familiar faces. Welcome, welcome, welcome. Now, dry ice, you might remember, is not made out of the same stuff or the same material or molecules as regular ice, the ice that we might get out of our freezer or buy at the grocery store. Now, normally we think of ice cubes as this stuff right here. This stuff is frozen H2O or frozen water, right? This is the kind of ice that we put into our drinks to keep them cold. We put it into our coolers to take things on trips. This ice we're pretty familiar with, our frozen H2O. Now, I'm going to go ahead and get out a little bit of our dry ice, and I want to see if anyone can use their prior knowledge, maybe Kyrie, Evan, Haley, who's tuning in on Facebook. Can you tell me if dry ice is not made out of frozen H2O or water, what is dry ice made out of? What type of molecule or what sort of substance? We keep our dry ice here inside one of these handy dandy coolers just to keep it nice and frozen there. And we'll talk about why that's important as we move through our program. But let me go ahead. I'm going to get out another beaker that looks pretty similar to the first one that we had. And we'll just go ahead and take a scoop, get a couple of our ice cubes. You know, even we could use one of our spoons here. That might be an even better idea. And we just want to first make some visual observations about our dry ice. So if we take an up close look, say if I zoom back in with my camera, at first, they look relatively similar, right? Our frozen H2O, our water ice, and our dry ice, they look very similar. They're both whitish in color to the eye. I'll tell you that they're both very cold, but you'll notice that I didn't need my fancy blue cryogenic gloves to interact with our regular water ice. We interact with that all the time. But I did put on my special cryogenic gloves to deal with this dry ice. Now, I have a couple people telling us, Evan from Texas and Christy also told us that this dry ice is made out of frozen carbon dioxide, which sounds very, very cool, and it is. But carbon dioxide is all around us. It's in the air that we breathe, but it's especially in the air that we exhale. So if everyone tuning in right now at home goes ahead and you take a big deep breath and exhale, you just exhaled a good amount of carbon dioxide. It's actually a byproduct or a waste product of all the metabolic processes happening inside your body all the time. We breathe in oxygen and out carbon dioxide. So oxygen acts as fuel for your muscles, for all of your different processes like digestion, and then we exhale carbon dioxide as waste. Now, we said that I had to wear these special gloves because dry ice is much, much colder than regular ice. We're probably familiar that water, or H2O, freezes at about 32 degrees Fahrenheit or 0 degrees Celsius, which is why the metric system is pretty cool. 0 is a pretty easy to remember number. But carbon dioxide only turns to a solid ice cube if you can get it to be negative 109 degrees Fahrenheit. That is super cold. Certainly colder than cold weather that we would ever experience outside. And so this stuff is far too cold for me to touch with my bare hands. If I were to touch one of those ice cubes, it might burn me or sting me pretty badly. So anytime I actually touch the ice itself, I'm gonna go ahead and put on these goggles, or not goggles. I'm gonna go ahead and put on these gloves. Now I'm putting on the gloves now because we are gonna set up one experiment to talk about why we call this substance dry ice. Now, we have regular ice and dry ice next to each other, and I'm just going to take one piece of each and put it down into our smaller cup. The smaller the better, because our goal is to just let this piece of ice go through that change in its state of matter as our program goes on today. So we'll try to pick some that are relatively the same size, or I might have to choose a few pieces of dry ice in order to kind of equal the size of our water ice here. But all we're going to do is, this is our exact experiment. All we're going to do throughout our program today is we're just going to let these ice cubes change. Now, we're pretty familiar with what happens to water ice when we leave it out on a hot day. It goes through a change in its state of matter. Now, what do we call ice going through a change in its state of matter when it gets warm? Especially if we're talking about water, we would normally refer to this process as melting. So where we see these arrows on this diagram here on the screen, that represents a phase change, a physical change, or a change in a state of matter. When solids turn into liquids, we call that melting, which is what water ice does when it gets warm. Now, if we take a liquid like water and we get it even warmer or add more kinetic energy or more heat, that will start to go through another phase change where it turns into a gas. And we call that phase change evaporation. And Evan told us that water boils at 100 degrees Celsius. So again, in Celsius, right, that state of matter, that change in our state of matter is really easy to remember. So water will freeze at 0 and evaporate at 100 degrees Celsius. A little bit trickier when we're talking about Fahrenheit, right? We know it has to be about 296 degrees Fahrenheit. Definitely not as pretty as a number as 100, right? So the metric system definitely gets some things right when it comes to science. So we'll go ahead and we're just gonna set those two cups off to the side, and we'll come back to those throughout our program. But we've also talked about some different properties of our states of matter as they start to change. All of these processes are reversible. You'll notice that the arrows go in either direction, that we can have solids turning to liquids, liquids turning to gases, gases turning to solids, but all of these arrows go in reverse. We can actually have a solid turn into a gas directly without ever melting and turning into a liquid first. And that's exactly the change that our dry ice goes through as it starts to warm up. Dry ice has to be negative 109 degrees Celsius in order to exist as a solid. If it gets any warmer, it actually skips that liquid phase altogether and goes right back to being a gas like we experience in the air all around us. We call that process sublimation. And so sublimation is reversible as well. That's actually how we make dry ice. We don't freeze it, or we don't condense it to a liquid and then freeze it into an ice cube. What we say we do is actually take carbon dioxide gas and make it cold enough under enough pressure that it turns directly to a solid, which has another exciting long name called desublimation. Maybe the scientists got a little bit lazy on that one, calling it sublimation in one direction and desublimation in the rest. But that's okay. Scientists can't always be the most creative people. But all of these processes are reversible. Now, we can see if we take an up-close look at these molecules, that our molecules start to behave differently based on the state of matter that they exist in. In a solid, those molecules are very, very tightly packed together. and they don't have a lot of energy to move because they're so cold and because they lack a lot of that kinetic energy. These molecules do move, but only slightly. They do almost like what we would call a vibration. Now, when we turn things to a liquid, you can see that those molecules, whether this is carbon dioxide or water or any other substance, those molecules start to spread out. And in a liquid, we describe their movement as flowing. So they still remain in contact with each other, but they're always in this kind of fluid motion, mixing around, pushing back and forth against each other. And a property of a liquid is that they will fill whatever space they are in or whatever container they are in, such as the cup. Now, as we go to our last state of matter, our gases, we're ignoring plasma for the sake of this discussion today. As we turn into a gas, those molecules start to move even more quickly. They spread out, and those molecules don't want anything to do with each other. They want to be as far away from each other as they possibly can. They move very, very quickly, and so those states of matter have a lot of energy. But let's go ahead and take a look at this in action, because it's one thing to see it on screen, but it's another thing to see it in practice. So what I have down here on this tray is an Erlenmeyer flask, which is the name for this kind of triangular shaped beaker. This is an Erlenmeyer flask with a rubber stopper at the top to plug it. And then you'll notice that this one is fancy because it just has this kind of rubber hose coming off the side. Now, if we drop a piece of our dry ice, that frozen carbon dioxide, into our Erlenmeyer flask down into that warm liquid, that solid starts to sublimate. It starts to turn into a gas. Now, carbon dioxide gas is invisible. We can't actually see it. But you do notice this kind of fog starting to form. And this fog is exactly what I said it is. It is actual fog. It is condensed water vapor, because even as this carbon dioxide turns into a gas, it is still much, much colder than the air around it. It could still be negative 100 degrees Fahrenheit. It could be negative 50 degrees Fahrenheit. It could be 0 degrees Fahrenheit. All of that, right, is cold enough to start condensing the water vapor in the air and turning it into a small cloud. Now we're going to go ahead and I'm going to plug our beaker here. And I want us to observe kind of the motion or the expansion of these molecules, because we said as this ice cube down at the bottom starts to sublimate or turn into a gas, those molecules are spreading out. And the easiest way to demonstrate that is by showing you how you can use dry ice to make some bubbles. Now let's see if I put enough in, or we can always add more. But you can see that this dry ice is starting to fill some pockets full of soap and starting to expand. Now, the piece of dry ice that I put in the bottom of the beaker, you can even see it down there, is very, very small. But we say that the expansion ratio of dry ice is over 700 to 1, meaning that dry ice takes up, or that carbon dioxide takes up 700 times more space as a gas than it does as a solid. So that's way more space. So in theory, if we let this entire ice cube sublimate, we could create 700 bubbles, the size of that piece of dry ice down at the bottom, as long as we trap all of it inside this gas and try our best not to let it escape. So that state of matter is expanding, and we can make even more, right, if we give it even more dry ice. So if we add even more pieces down in there, we have even more sublimation, a little bit more of a rapid expansion now. And we fill our bubbles much more quickly. So again, taking up much more space as those molecules of carbon dioxide go through that phase change, turn from being a solid into a gas. Now I have another of my favorite experiments set up here. In this bowl here, I have just a small amount of water down in the bottom of the bowl. You can't see it, but I promise you it's there. You can see my hands are nice and wet. And we're just going to do the same thing. We're going to take some dry ice, drop it down inside the bowl here. You can see that nice puff of water vapor starting to form. So we know that that dry ice is starting to sublimate. And what we're going to do is this time, we're actually going to trap this inside using a bigger bubble. In order to make a bigger bubble, we need something bigger than our hose there. So let me zoom back down, but only ever so slightly because I want you to be able to see the entire procedure here. All right, we're going to take a piece of paper towel, and I'm actually going to dip the whole thing down inside our beaker of soapy water. Then we're just going to pick it up, let all of that excess liquid kind of drain off of our paper towel here. And we're going to use this kind of like a sheet in order to try to trap the gases inside a bubble. And this takes a little bit of practice, but bear with me here. I need a little bit more soapy water. Nice and soapy. Not quite. Oh, there we go. I think it would help if my bubble wand, my makeshift bubble wand at least, was a little bit flatter. Let's try a new piece. Always come prepared with a backup, but we'll go ahead, we'll dip this down inside. Let it drain. No one said that science can't be messy. I know that it almost always is when I'm the one doing it. And the cool thing about dry ice and all the experiments that you see here is that dry ice you can actually get at a grocery store. So unlike some of the other kind of dangerous chemicals that we work with when we do other experiments here on the show, this is something that's pretty easy to purchase on your own. So you can actually get dry ice at most major chain grocery stores. You can actually get it at places like Meijer if you have a Meijer, if you're local to Michigan, or you can get it at Walmart as well. If you just ask someone at the desk where they keep it, it's usually near the customer service line, and they sell it at grocery stores to keep your camping stuff colder for much longer. And so you can get it year round, and you can actually try some of these experiments at home. But keep in mind that this dry ice is very, very cold, like extremely cold. So make sure that you have an adult to help you out and that you're being safe by using a pair of gloves. They don't have to be cryogenic gloves like this, but just your winter gloves or a pair of work or gardening gloves would be enough to help keep your hands safe. Now, take a look at our giant bubble that's starting to form. Now, our handful of dry ice is still steadily sublimating down there at the bottom. But instead of letting that gas escape, which of course now it did that right as I gave it too much attention, right? That bubble was starting to form. Let's add even more dry ice. Maybe we'll have better luck. All right, a ton of dry ice down in there now. Hopefully it'll fill our bubble a little bit faster. There we go. All right. And with our gas starting to sublimate, starting to fill this bubble, this is one of my favorite experiments to do at this time of year because I think it looks almost like a crystal ball in honor of Halloween, one of my favorite holidays. Now, that gas is being trapped inside, right? And as long as the bubble can take the pressure, that bubble will keep expanding. It looks pretty cool. You can even see kind of that iridescence, that rainbow that we see on the bubble until the pressure becomes too much and our bubble starts to pop. Now, we've got lots of soap bubbles in here. So I'm going to go ahead and set this off to the side. But I have one very last experiment to show us to talk about the expansion of these gases. Now, what would be the point of talking about a rapid expansion of gases unless we were to throw in something like an explosion, right? We did have technically an explosion when our bubble popped, right? That was our closed container. And the rapidly expanding gas inside, right, grew and grew and grew and built pressure until the container it filled couldn't take it anymore and it popped or it exploded. But we'll bring out one of our favorite containers to do explosions in. You might recognize this from our carbide cannon experiment. Only difference with this one is there's no hole poked in the back so that we can start a fire. This time we're just going to use our dry ice in order to cause this explosion. We'll take just a couple pieces of our dry ice, toss it down inside, let that start to sublimate as it reacts with the tiny bit of warm water that I put down in there before the program. Go ahead, pop on the lid to create our closed container, and let's let the rapid expansion of gas take over. Dun, dun, dun. Look at that. Our lid goes pop, right? As our rapid expansion of gases takes place, the pressure builds until the lid goes popping right off. Now, Again, this is an experiment that you can and you should try at home if you are able. All you'll need is a coffee drinker in your life that's willing to give you a closed container. Now, never replicate this in something that has a screw top lid, right? Because that lid is not going to come off easily. That could create a much more dangerous explosion. If you're going to try things like this at home, we always want to consider safety first, right? And so pick a container that has a press-on lid, something like a Tupperware would work, or anything that has that kind of press and seal lid, not something that's made of glass, and not something where the pressure won't be able to escape safely. So blow things up for the sake of science, but again, safety first always. Try that one at home. Now we've got just a couple more experiments left to go. One of my favorites is this one right here. We've seen this one before in our colorful chemistry episode, but in this beaker is not food coloring. I know that I have all sorts of crazy liquids here on the table, but all of these ones that you've seen that I was using to sublimate my dry ice earlier, all of those are just food coloring and water, especially if we take a look at this one. Maybe we'll use that for a comparison for our experiment here. But this yellow one over here, that's just food coloring. Our blue one over here, food coloring as well. The red one down here inside our fancy little container, still just food coloring with water. And it's just a good vessel for starting to sublimate that gas much more quickly than it does when it just reacts with the air. But inside this beaker is something a little bit different. It's a substance that we've used before. This one is called universal indicator. This is something that you probably don't commonly find at the store or the grocery store, wouldn't really have access to at home. This we do buy from a chemical company, but what this tells us is the pH of the liquid or the substance that you mix it with. If you think back a few episodes, or wow, it's been quite a few episodes now since we've talked about the pH scale, but the pH scale tells us whether something is an acid or a base. So acids are red on the pH scale, and we're pretty familiar with acids, right? That when we think about things like battery acid, that acids can be very, very strong and very, very corrosive or dangerous. Oh boy, I hope I'm pointing in the right direction. You'll have to tell me if I'm not, as I think about, oh, I am. There we go. So acids are dangerous, and bases are the complete opposite, right? So when we have a pH of 0, that's a strong acid. But if we have a pH of 14, 14 is a very strong base. Now think back to what we've talked about acids and bases so far. If they are exact opposites when it comes to the pH scale, and acids are very dangerous, does that make bases safe? Tell me what you know about bases. Or even better yet, if you remember an example of a strong base, something that has a pH way over here close to 14, which if we were to mix it with our universal indicator would turn very, very dark blue or almost even purple. Tell me what you remember. Does anyone remember an example of a strong base? Now we talked about acids, right? I know if we think about common acids, we can think about things like battery acid, or your stomach is full of acid, and you actually even have some weak acids inside your mouth that start to break down your food as you start to chew, and masticate is what we call that in terms of science. But lemon juice and orange juice are also examples of acids. As we shift over to the opposite side of the scale, weak bases would be something like dish soap, like the soap that we used for our bubble making experiment. So dish soap is an example of a base. If we go maybe a little bit stronger, we might find something like baking soda. If we go even further, though, we start to find things like bleach, or even further, something like drain cleaner. So bases, even though they're the opposites of acids, are just as dangerous. They are just as corrosive. The only things that we consider to be safe, or at least food safe on the pH scale, are right where I'm standing, right here at a pH of 7, things that we say are neutral. And you might notice that here inside our beaker, right, I have some sort of neutral substance, right? Inside my beaker is just water mixed with that pH indicator. Now, since I added the pH indicator, that would make this water not safe to drink. You definitely don't want to drink pH indicator. It tastes really nasty, I'm sure, because it has kind of a smell to it. But there are all sorts of warning labels on the bottle as well. But we know that the substance I mixed it into was at least neutral to start because of its green color. Zoom in just a little bit here. Ooh, opposite of what we want. Way too zoomed in. There we go. But let's watch as we see a pretty dramatic shift, and we'll leave our green water here. Now remember, this one is just food coloring, but we're gonna add a piece of dry ice to each. And I want us to watch as we let that dry ice or carbon dioxide sublimate inside our beaker. Let's take a look at what happens to the pH. I'm starting to notice a difference already. Our dry ice is turning this liquid, our water inside the beaker, into something else, right? This is certainly no longer neutral. This is no longer something that is safe to drink. This is now shifting in one direction on our pH scale. Based on what I showed you, what would you call this substance now? It's definitely not neutral, but is it an acid or is it a base? So take a look at the scale behind me. Remember that red was something like battery acid and purple was something like drain cleaner. Reds are acids, blues are bases. Reds are acids, blues are bases. And so what we've created down here inside this tall graduated cylinder is definitely acidic. This stuff is turning into carbonic acid, which is actually pretty corrosive stuff. But unfortunately, people drink carbonic acid all the time. This carbonic acid is the same stuff that you find inside carbonated beverages, whether that's seltzer or whether it's soda. Even though we consider seltzers to be better for us, right, because they're pretty low on sugar, they're still very acidic, and that acid is really bad for the enamel coating on your teeth and kind of the other organs inside your mouth. So if you've ever wondered why your dentist tells you to avoid drinking carbonated beverages, even if it's seltzers, this is why. That carbonic acid is in all of those substances that you drink. Now, of course, everything in moderation, right? Everybody wants to enjoy a little bit of carbonation every once in a while, but keep in mind that this is damaging to your teeth. So if you do choose to drink carbonated beverages, make sure you brush your teeth really, really well afterwards. Just a PSA, as always, from me right here at the Michigan Science Center. Now, I have one last experiment to try that I saved for last, but if anyone has any questions before we head out, feel free to let me know in the chat. I see lots of friends telling us that they do not drink soda or seltzer. I see that Evan does not drink soda or seltzer, and that is awesome. Don't start now. Keep your teeth nice and pretty and white forever and ever and ever. But if you do have any questions, feel free to ask them in the chat. I'm keeping an eye on those as we kind of finish up our program here. Now, this last one, I'll need to kind of move around my microphone just a little bit because we talked about how as dry ice sublimates or turns into a gas, it starts to expand. Now, if we take a look at our first experiment, we can see that both of our ice cubes here, both our H2O ice cube and our dry ice cube, both of them are starting to disappear or at least shrink down in size. But what you'll notice is that in this beaker, let's see if I dump them on the table, I want you to notice that there's a big difference between what just came out. From our water ice, which is safe to touch, we've got a huge puddle of water, right? So we can see the liquid that's formed as this one starts to warm up. Our dry ice, right, we said skips that liquid phase altogether. So there's no puddle. It's fantastic. I have very little cleanup to do when it comes to that ice cube right there. So go ahead, pop those off to the side here. And let's get going on our very last experiment. Now I brought with me 2 metal spoons today because I want us to be able to maybe even hear the evidence of this sublimation and of this expansion of gases instead of just being able to see it. Now, let's see. Like I said, I'm going to have to move my microphone. I'm actually going to try to clip my microphone here to the spoon. So we'll see. I practiced this earlier, but it is a little bit finicky, meaning just a little bit sensitive, only works not very well. So hopefully you can still hear me. I'll make sure I talk nice and loud. But we're gonna go ahead using one of our spoons here, still making sure not to touch it with my hand. I want you guys to tell me, can you hear this noise? I'm gonna hold it away for a second and then I'm gonna bring it back in and tell me, can you hear anything? That's working really well. Get a new piece. Let's see, and in practice, it actually worked better if I put some pressure on them. You should be able to hear, in theory, still hear my voice, you should be able to hear some vibrations or kind of like this tingling. Yeah, I'm seeing some people, they're telling me they can hear it. Let's try that one more time. What you're actually hearing is the vibrations of those atoms and molecules as they try to escape their solid form. We said that those molecules are expanding. They're taking up more space. And so even on a microscopic scale, even in the amount of space between the solid ice cube and the spoon, we can actually hear those vibrations. As that turns into a gas, it's actually pushing and knocking and banging on the spoon, almost knocking like knocking on a door. Let's try that one last time. That was actually a really good one. So we can actually not just see the evidence of that sublimation and that expansion that takes place, we can actually hear it too. All right. No questions coming in the chat just yet. If you do have them, still feel free to ask. But as always, since this is just about the end of our dry ice episode of Echo Live, we want to be sure, as always, to make sure we thank the sponsors of Echo Live. Ford and Denso are making sure that we still continue to bring Echo Live episodes to you, learning at home or in your classroom for the rest of the year. Again, you can catch our show on Wednesdays at 2:30 p.m. Eastern. So if you're in Texas, that's 1:30 p.m. Eastern. And if you can't tune in live, don't worry, we will still continue to post our recordings on our Facebook and our YouTube channel after the show. So you can still watch them. You know how to reach us if you have questions, or if you're looking for more science that you can try at home after the program. Take a look at our website, mi-sci.org/at-home-science. We've got all sorts of activity guides for you to try. If you try any of them at home, make sure you take a picture and send them to us so that we can see. All right, that is just about the end of our program here today. Thank you all so much for joining, and I'll see you back here next Wednesday for another exciting episode. I see those recommendations coming in. A heat engine, very interesting idea. And I will be sure we get that on the calendar for you. So check back in. See you all next week and have a great weekend. See you later.